Okay, let's just dive right in. Welcome to today's explainer. We're tackling what is literally the ultimate tool for finding the shortest path in an unweighted graph. Breadth first search, or BFS. If you've ever wondered how your GPS finds the fastest route without a hitch, or how a network routes data packets so incredibly fast, well, you're looking at the foundational logic right here. Real quick, here's our roadmap for today. We'll start with an intro to Graph BFS, then look at the core BFS template. From there, we'll cover tracking the shortest path, multi-source and the 0-1 matrix, level-by-level BFS, and wrap it all up with your ultimate BFS toolkit. All right, let's get into Section 1, Intro to Graph BFS. To really get this, we first have to understand how Graph BFS is fundamentally different from Tree BFS. It's a make-or-break distinction. With a tree, you're just flowing straight down. There's no way to loop back. But graphs are a bit messier. They can have cycles. If you're exploring neighbor by neighbor and you hit a path that loops right back on itself and you aren't tracking where you've been, well, you're going to be stuck in an infinite loop forever. That's why you absolutely have to track your visited nodes. It is your mandatory safety net. Moving right along to Section 2, the core BFS template. Now that we know the danger of cycles, let's look at the actual blueprint. It's honestly beautifully simple once you break it down into these 4 steps. Step 1, you just initialize a Boolean visited array to track exactly where you've been, plus a queue. Step 2, toss your starting node into that queue and immediately mark it as visited. Step 3 is the real engine. While your queue isn't empty, you pull or remove the current node. And finally, Step 4, look at all its neighbors. If a neighbor hasn't been visited yet, mark it true and add it to the queue. That's the whole foundation. Process nodes, explore unvisited neighbors, and just keep going until the queue is completely empty. Which brings us to Section 3. Tracking the shortest path. Let's see how this basic template adapts to solve actual shortest path problems. The logic is incredibly elegant. The distance of the neighbor equals the distance of the current node plus 1. Seriously, that's it. By just adding a distance array to your template, you track the exact shortest path. Since BFS explores outward uniformly in every single direction, the very first time you hit an unvisited neighbor, you are mathematically guaranteed to have found the absolute shortest path to it. You just grab the current node's distance, add 1, and you're good. It's a total game changer when a problem asks for the minimum steps to hit a target. On to Section 4, multi-source and the 0-1 matrix. So, what happens when you have more than one starting point? Think about dropping a handful of stones into a perfectly still pond, all at the exact same time. Multi-source BFS works exactly like that. Instead of just one start node in Step 2, you load up your queue with every single source node right at the beginning. A great real-world example is predicting how a forest fire spreads from, say, 3 different lightning strikes at once. You let the search radiate outward from all sources simultaneously. Whichever ripple hits a target node first, boom, that's your shortest path from any of the sources. Let's ground this with a classic problem, the 0-1 matrix. Imagine a grid completely filled with zeros and ones. Your goal is to find the minimum distance from every single cell to the nearest 0. Now, if you try to run a standard single-source BFS from every individual one just to hunt down a 0, you're going to end up doing a massive amount of repeated, totally inefficient work. So how do we flip the script to fix this? It's brilliant in its simplicity. You just add all the zeros first. Treat all the zeros as your multiple starting sources and dump them all into your queue right at the start. Then, let the BFS radiate outward towards the ones. The very first time your search hits a 1, you instantly know you found the absolute shortest path to it from the nearest 0. It's a fantastic way to optimize what looks like a really complex grid problem, using that exact same basic template. Next up, Section 5, level-by-level BFS. Sometimes you don't just want a path, you need to process the whole graph exactly one layer at a time. Think of LinkedIn. You want to find all your first-degree connections before you even start looking at your second-degree connections. But here's the tricky part. When you're traversing level by level, how do you know exactly how many nodes actually belong to the current depth before you accidentally start processing the next layer down? Because remember, our loop is constantly tossing new neighbors into the back of the queue. The fix for this is so simple, it's genius. You just take a snapshot using queue.size at the very start of each level. Before you pull a single thing out of the queue for that specific layer, you check the size. If the size is 5, you run an inner loop to process exactly those 5 nodes. Sure, processing them is going to add a bunch of second-degree connections to the end of the queue, but your inner loop safely stops after 5. This guarantees you process the graph perfectly, depth by depth, without ever mixing up the layers. And finally, Section 6, your ultimate BSF toolkit. We've covered the foundational blueprint, and we've walked through real examples like multi-source and level-by-level traversal. I absolutely love this quote from the source material. BFS template is short. Memorize it, use it for any shortest path and unweighted graph problem instantly. That is the ultimate takeaway here. You've got the core algorithm, you know how to track distances, handle multiple start points simultaneously, and process layer by layer. So the next time you're staring down a massive, complex network and need the absolute fastest route, are you going to get lost in the weeds, or are you going to drop in this simple blueprint and map it out instantly? Thanks so much for joining me on this explainer, and I'll catch you next time.